There are a variety of definitions for acid and base. Some are very specific and others quite general. Let's start by talking about the Bronsted-Lowery definition. A Bronsted-Lowery acid donates a proton, whilst a Bronsted-Lowery base accepts a proton. Let's see this in action with a generic example. On the left-hand side, A stands for acid and B stands for base. If we follow the mechanism arrows, we will see that the base is taking the hydrogen and the acid is giving the hydrogen in the form of a proton. This results in the base becoming a conjugate acid and the acid becoming a conjugate base. The conjugate acid is neutral if the base is negative and positive if the base is neutral. The conjugate base is neutral if the acid is positive and negative if the acid is neutral. The arrows in between the left-hand molecules and the right-hand molecules seem different from what we've seen before. Reactions have a single line with a single double-barbed arrow, whilst the arrow in between resonance structures is a single line with double-barbed arrows on either end. Here, there are two lines with a single barb on each end. The different molecules on left and right are in equilibrium. If we think about some specific cases, such as the strong acid hydrochloric acid, we would expect to see more molecules on the right-hand side. A weaker acid, such as acetic acid, would give us fewer molecules on the right-hand side. Let's take hydrochloric acid as our acid. So we're replacing the letter A with Cl. What about the base? Well, water is a very important base, so we will replace B with H2O. The same thing's going on. The water takes a hydrogen in the form of a proton to become hydronium, whilst hydrochloric acid is giving up a proton to become a chloride. Now, in this specific case, the equilibrium is constant, and for each specific set of molecules, you would have a different constant. How can we measure the equilibrium constant? Well, let's go back to our generic example HA, but we're going to keep water as the base, as it's our standard base for these calculations. We're talking about more on the right-hand side or less on the right-hand side. So it's a quantity we want to measure, and we do that in concentration. So the number of moles per liter. We express concentration by drawing square brackets around a molecule. But what is the equilibrium constant for the reaction of hydrochloric acid with water? Well, what we do is to take the concentration of the molecules on the right-hand side and multiply them together, and divide that by the concentration of the molecules on the left-hand side that have also been multiplied together. So we have the concentration of A minus multiplied by the concentration of hydronium, H3O plus, and we divide that by the concentration of HA multiplied by the concentration of water. Now, water is constant. It's always the same concentration of 55.6 molar at 25 degrees Celsius. It would be really useful to remove water from the equation because remember, the equilibrium constant is different for each case. And if we have water there, that's always the same, and it's adding more work to making the calculation. So, how do we go about removing it? We multiply both the left-hand side and the right-hand side by the concentration of water. And the water on the right-hand side is cancelled out, whilst the left-hand side becomes the concentration of water multiplied by the equilibrium constant.